In this video, we'll practice calculating volumes by integration. We'll be starting with an area, say a quarter circle, and revolving around an axis, let's say the y-axis, and what we'll be producing is a solid. In this case, we would be producing the top half of a solid sphere. And our goal is to calculate the volume of this solid. Now there are a couple ways to calculate the volume. Let's start with our area. Let's think about the axis that we're revolving around. If we take a slice perpendicular to the axis that we're revolving around, and we revolve that slice around our axis, what we're going to be creating is a very thin disk. So it's a solid disk. You could think of it like a pizza, but infinitely thin. So it's circular, very thin. And dV is going to represent the volume of this solid disk. All right, so because it's circular, it's going to have area, pi r squared, so pi times radius squared. But because it's three-dimensional, we need to also multiply by the thickness. So dV, the volume of this solid disk, pi times radius squared times thickness. Now to find our volume, we'll be integrating dV with appropriate limits of integration. Now here's a second way to calculate the volume. So again, we could think about our area, think about the axis that we're revolving around. And we could take a slice parallel to the axis that we're revolving around. Now if we revolve this slice here around our axis, again we're going to be creating sort of a circular shape. We're going to see that slice being revolved around here, so we're going to get this sort of a shape here. And what we're creating is a hollow shell. So I think of it sort of like a can of soup with no top or bottom. So we've just got the side of the aluminum can, and it's infinitely thin. Now if we're imagining this very thin, hollow can of soup with no top or bottom here, let's think about how much metal we would need for that can, so that would be the volume of this hollow shell. Well, we would need to build the circumference here, so that would be 2 pi times the radius. We would need to multiply by the height, so that would be this dimension here, and then multiply by the thickness of the metal, meaning the thickness of this hollow shell here. So dV would be 2 pi times the radius times the height times the thickness just being that tiny little dimension there. And then to get our volume, we would integrate dV with appropriate limits of integration. Let's consider the solid generated by revolving the first quadrant region, bounded by y equals x squared, y equals 0, x equals 3, about the x-axis. We'll find the volume using both the disk method and the shell method. Well, let's start by drawing a sketch of the first quadrant region. So the curves that are going to be bounding our region, we've got y equals 0, which is our x-axis. We've got x equals 3, so I'll put that on the picture. And we've also got a parabola, and let's point out that when x is equal to 3, y is equal to 9. So I'm just going to label that here. So that point would be on our parabola, and that parabola would be passing through the origin. So we've got this curve here, I'll label it, y equals x squared, and we've got the vertical line x equals 3 as well as the x-axis. Okay, so there's our first quadrant region there. And we're going to be revolving this about the x-axis. So we're going to be revolving this way. So let's see if we can visualize the solid that's being created. I'm going to draw it a little bit smaller. I'm going to draw it away from the coordinate axes here. So we'd have this circular area at the right side here. And we're creating this solid shape that looks like this. And we'd like to calculate its volume. So part A, let's calculate the volume of this solid using the disk method. Well, I'm going to very quickly just redraw our sketch. Okay, so we've got all the important facts labeled there, and we are revolving about the x-axis. Now for the disk method, you want to take a slice perpendicular to the axis of revolution. So there we go, we've got a vertical slice. And you want to picture the disk that's being created as that vertical slice gets revolved about the axis. So initially the vertical slice is right here, and as it gets revolved, it's going to be tracing out the top part of that circle there. And because that vertical slice has a little bit of width or a little bit of thickness, you're going to have a little bit of thickness to this disk here. So let's think about the dimensions of our disk. The radius of this disk here is going to be represented by that dimension there, which will be y, and the thickness of our disk is going to be dx. So when we work out dv, in general for a disk, dv is going to be pi times the radius squared times the thickness. And for this particular disk, dv will be pi times y squared times dx. So at this point we know that we're going to be integrating with respect to x. So we can then say v is going to be the integral of pi y squared dx, and because we're integrating with respect to x, the limits of integration have to be x values. So if we look back up at our area here, it's ranging from x equals 0 to x equals 3. All right, now to complete our integration, we need to get y squared written in terms of x. So let's look back up at our sketch here. Remember that y is equal to x squared. So as we plug in here, we're going to have a volume equal to the integral from 0 to 3 of pi times x squared squared dx. So notice that y is equal to x squared, and then y is being squared in this formula. So it's actually x squared squared that we're getting in this integral here. All right, now to get on with the calculation, let's bring the constant pi out in front. We've got pi times the integral from 0 to 3 of x squared squared is going to be x to the 4th. So we'll be integrating that with respect to x. Now we're ready to do our integration. V will be pi times the integral of x to the 4th is going to be x to the 5th over 5, and that'll get evaluated at 3 and then at 0. So v is equal to pi times 3 to the 5th over 5 minus 0. So you could say v is equal to 3 to the 5th pi over 5, or if you prefer to write that as a decimal because it is exact as a decimal, you could say 48.6 pi.